Okay, so I'm happy to welcome all of you here. I'm Alexander Kordyuk and represent Kyiv Academic University now. Also this project, GUKUMAT project, which is German-Ukrainian Center for Quantum Material Research, which is funded by German ministry. It was BMBF called. Now I usually forgot how its correct name. Could you? Yeah, okay. We are grateful for this support and this project. In this project, we are building a German-Ukrainian center in Ukraine. And topic of this project is theory-assisted search for new quantum materials. And theory-assisted, this means that theoretical part is essential part of our research. And here, this is already second meeting, second workshop. It is which is mainly theoretical, started from theoretical. It was first in Kyiv last year, was devoted to altermagnets, which we call unconventional magnetism, to keep it as wide as possible, wider, a bit wider, better to say. Now we also add superconductivity, unconventional superconductivity, taken in mind mainly firstly topological superconductivity, but also to keep it open. And now we are hosted by Lviv National University, Ivan Franko National University, yes. And we are grateful for this hospitality and for the help. Now this is, I think they better tell something, a few words about this, right? So I give the floor to you just for a short welcome. And you maybe tell us about this building and so on, yeah, a bit.
Okay. Good morning, ladies and gentlemen, Professor Van den Brink, Professor Kordyuk, dear colleagues, dear guests, dear participants of the workshop. Maybe I will start with introducing myself. My name is Khrystyna Miliyanchuk, and I am a Vice Rector for International Collaboration, but additionally, I have a background in physics and in chemistry, so it's my great pleasure to be here with you today. And in fact, the aspects of unconventional magnetism and unconventional superconductivity are also very close to my scientific and research interests. So it is my great pleasure to welcome you at the International Workshop on Unconventional Magnetism and Superconductivity in Quantum Materials here at Ivan Franko National University of Lviv, and we really appreciate our collaboration with the Kyiv Academic University. So in fact, this building is not a building which was intended for studying, for academic aspects, but for various representative meetings, and some international conferences of the highest level are being held here. And I do suppose that you will enjoy both the scientific program and also the sightseeing here in Lviv. So we are especially pleased to host researchers working at frontier of physics, chemistry, and material science, fields that shape both our fundamental understanding of nature and the technological future of the society. Addressing our international guests, I would like to express our sincere appreciation for your support, solidarity, and continued scientific collaboration with Ukraine and with our university as well. Meetings such as this workshop remind us that scientific collaboration is built not only on ideas and experimental results, but also on trust, on openness, and shared values. So thank you for your braveness to come here and to stay here with us. Ivan Franko National University of Lviv has a long tradition in the research of both functional materials and unconventional physical phenomena. Today, these studies are actively pursued at least at 2 faculties, and primarily the Faculty of Physics and the Faculty of Chemistry. Since the emergence of quantum theory, the work of our theoretical physicists has resonated with the most important developments in the world science. Many important discoveries connected with magnetic and superconducting materials originated here and became part of the global scientific landscape. At this point, I would like to mention at least one example, namely the compound cerium copper to silicon 2, which was first synthesized here at the Department of Inorganic Chemistry at Lviv University. In this material, the coexistence of magnetism and superconductivity was observed in 1970s. Phenomena long considered mutually exclusive. This discovery opened new directions in the physics of correlated electron systems and challenged fundamental aspects of superconductivity. Today, fundamental research is increasingly connected with global technological challenges, and in this context, quantum information science, quantum computing, and quantum programming successfully developed at the Department of Theoretical Physics are among those most promising scientific direction of the 21st century. This workshop provides an excellent opportunity to exchange ideas, establish new collaborations, inspire young researchers, and strengthen the international scientific community, especially during these challenging times. So I wish all the participants fruitful discussion, successful presentation, new scientific insights, and an enjoyable stay here in Lviv. So thank you for choosing us. Thank you for coming here. Thank you.
Thank you very much, and I want to welcome for a few words Jeroen van den Brink, who is actually initiator of these workshops and also initiator of many number of already programs to support Ukraine and collaboration between Ukraine and IFW, and starting from UKRATOP and Oleh and UKRAPRO, the project during which IFW hosted many peoples when war started. And now there's Gukumat and this particular already series of workshops. So it is mainly his work and his initiative. So please, Jeroen.
Thank you. It's not necessary. It's about science. Thank you, Vice Rector, for your very kind and appropriate words. It's about shared values. And I hope that we'll have a nice conference, nice workshop, where young people, the new generation and the old generation can interact, and we can push science and society forward in the ways that we envision them. Please, now, the first chairman will be Sasha. So, if you're ready, then we go.
Okay, very short. So Jeroen saved at least 4 minutes, so we can start from the talk of the host of this event, Oleh Bovhyra, and he will tell us a bit about university, right?
Hello, everyone. Dear colleagues, dear participants of International Workshop on Unconventional Magnetism and Superconductivity in Quantum Materials, dear young scientists. It is a great honor and pleasure to stand before you today. My name is Oleh Bovhyra. I'm representing Miliyanchuk University of Lviv. Today I would like to give you a brief overview of our university, its rich structure, and key research areas that drive our scientific community forward. Let me take a brief moment to welcome you to the city we call home, our Lviv. Lviv is the city where history meets the future. It's widely known as the cultural capital of Ukraine, famous for its unique architecture, cozy cobblestone streets, and of course the stone lines that guards our city's heritage. Lviv has always also been a powerful hub for education and science in Eastern Europe. Welcome to our Lviv. Our institution, the Ivano-Franko National University of Lviv, is founded in 1661. It is one of the oldest universities in Eastern Europe. We have 19 faculties covering everything from humanities to natural and exact science, 18 specialized scientific research laboratories where our teams conduct experiments. Our campus is spread across 30 historical and modern buildings, and our academic structure includes 140 departments, 9 institutes, and 7 museums that preserve our scientific legacy. We offer near 280 degree programs. We're hosting between 18 and to 100 academic conferences per year, much like the wonderful workshop we are attending today. Our scientific strength lies in our people. We are proud to have over 300 doctors of science and more than 1,200 philosophy doctors actively teaching and researching. The academic family guides near 25,000 students and employs 4,040 staff members. Let's look at our scientific output indexed in the Scopus database. This slide illustrates our publication subject trends, and I believe it speaks for itself. As you can see, physics and astronomy is our leading sector, accounting for 20% of all university publications. It is closely followed by material science and chemistry. If you sum this up, nearly half of our entire university scientific output is concentrated precisely in physics, chemistry, and material science. This distribution of scientific publications among different fields reflects our core research areas, which we have structured into 4 key pillars on this slide. First, material science and nanotechnology. This is where our famous Lviv crystallographic school shines. We focus on synthesis and characterization of new intermetallic compounds, predicting and developing new crystal structures, and analyzing advanced and functional materials. Second, fundamental science and informational technologies. Our theoretical physics group work extensively on quantum mechanics, quantum computing algorithms. About this, you were listened by Khrystyna in her presentation. Quantum computing algorithms, statistical physics, and also low temperature physics, quantum critical phenomena, nanomaterials, nanotechnologies. We also boast research in life science and ecology, and have deeply rooted tradition in humanities and social science. We have over 40 world-class research schools actively operated across disciplines. Having introduced the university profile, I would like to transition to the main part of my presentation. As we discussed and agreed with the organizing committee, rather than presenting a broad general overview of all universities' science, we want to focus especially on the areas that align perfectly with the theme of this conference. Therefore, our presentation today is structured around 4 interconnected research areas. First, quantum materials. Here we talk about work in crystal chemistry and materials design, particularly synthesis of new intermetallic compounds and the exploration of strongly correlated electron system and topological phases. second, magnetism and superconductivity in quantum materials, and fourth, synchrotron studies. Here we talk about magnetic skyrmions that are topologically stable spin structures with a particle-like nature, and they are currently being intensively studied as candidates for information beats. We have investigated intermetallic compounds that serve as a host of skyrmion formation. We investigated the crystal structure and state diagram of ferrum germanii compound over a wide range of temperatures and external pressures. The structure of the ferrum germanii compound is not centrosymmetric and had a significant ferromagnetic region and the state diagram, which made its candidate for area of skyrmion formation. Here we have crystal structure of ferrum germanium. Figure 2 shows the change of interatomic distance with pressure and phase transition without changing of the crystal structure, and the phase diagram of the compound on the right. Skyrmions are formed in the ferromagnetic region of the compound state diagram, but the formation of antiferromagnetic skyrmions is also possible. A regular array of skyrmions crystal features the topological Hall effect of electrons that in turn gives rise to the Hall effect of the skyrmions themselves. It is commonly believed that antiferromagnetic skyrmion crystals lack both effects. We studied compounds and solid solution based on them in the multi-component system chromium, nickel, silicium in order to obtain new errands for ferromagnetic and antiferromagnetic skyrmions. They are characterized by non-centrosymmetric structures and non-centrosymmetric bulk magnets with achiral polar symmetry provide a good arena to study the topological and spin structure. Recently, a nanometric skyrmion lattice has also been reported for centrosymmetrical rare earth compound. We investigated a number of these compounds of composition, rare elements, cuprum and stannum. Among them, you can choose compound with both ferromagnetic and antiferromagnetic regions of the state diagrams. Here we have, in this work, we investigate properties of 3 quaternary alloy pairs with structure of aurum for aluminium. I don't have a laser pointer at the structure. This research aimed to create quantum materials for potential application in data storage and spectronics. All samples exhibit parametric behavior following by the modified Curie-Weiss law. Substituting small amounts of cuprum and ferrum or palladium for chromium and nickel weakens antiferromagnetic interactions, potentially enabling ferromagnetic ordering needed for skyrmion formation. Such compounds may present conductive media for nucleation of magnetic skyrmions. Or skyrmions, I will tell this term, skyrmions. Interesting for physical experiments are compounds with quantum phase transitions near temperature of absolute 0. These transitions are performed using the energy of quantum fluctuation. Such a transition to the antiferromagnetic state was recorded by us for the compound in the homogeneity region, dysprosium, cuprum stannum. Another work have titled Hydrogenation as a fine tool to tune magnetism. Metal hydrides are usually considered as efficient hydrogen storage media with high volumetric and gravimetric hydrogen density. Yet, hydrogenation proved to be a fine tool to tune magnetism in intermetallics. Here we study various structure-related compounds from the point of view of hydrogenation. Hydrogenation leads to the lattice modification, which is anisotropic in many cases. Apart from bringing an additional electron and forming new chemical bonds in the initial compound, the interatomic distances are changed, which has an impact on the magnetic properties of intermetallics. In the compound with the pure localized magnetism, we can observe even dramatic suppression of magnetic ordering. The example of this slide demonstrates compound with the magnetic contribution of D metal, which allows gradual variation of magnetic ordering temperature. The presented results discuss the possibility of using thin magnetic films composed of single domain magnetic nanoparticles with axial anisotropy for directional absorption of microwave radiation. It especially identifies that energy dissipation is maximized when the external field aligns with the hard magnetization axis, and finding crucial for controlling heat signatures in spintronic quantum devices. The results highlight how structural symmetries dictate the efficiency of energy transfer, providing a quantitative framework for predicting the stability of unconventional magnetic textures in hybrid superconductor magnet system. Here we have the compounds such as barium, iridium, silicium, and strontium, palladium, silicium are the quintessential quantum materials characterized by non-centrosymmetric crystal structure. This structural asymmetry introduces strong antisymmetric spin-orbit coupling, leading for unique superconducting state where a singlet and triplet Cooper pairs coexist. By investigating these phases, researchers can explore the fundamental physics of Rashba split electronic bands and their potential for hosting topological and non-trivial phenomena. Also, transitional metal borids composed of various metal elements attracting attention in different areas of research for their superconducting and magnetic properties. The compound cuprum-iridium-bor and cuprum represent a promising class of quantum materials that feature a delicate interplay between strong spin-orbit coupling and electronic correlation. Specifically, cuprum-iridium-bor is theoretically predicted to host non-trivial topological phases, such as nodal chain semi-metal state protected by crystalline symmetries. Meanwhile, the non-stoichiometric cuprum-iridium-2 bor2 minus X exhibits superconductivity, making this system highly attractive for exploring and coexistence of topologic and macroscopic quantum phenomena. And another area of my presentation is about synchrotron studies. Synchrotron research is the key tool for studying materials, especially quantum ones. Several of our research groups conduct studies at the European synchrotrons, and we work very close with DESY, research by Luminescence laboratory team at the DESY German Synchrotron Center in Hamburg vividly illustrates the integration of Ukrainian science into the global research area. For example, the Luminescence laboratory team has become one of the leaders in researching of the ultra-fast radiative decay of electronic excitation, specifically core valence luminescence. Discovered effect upon the transition from bulk crystals to nanoparticles, for example, fluorides, halides, or phosphates, a decrease of intrinsic luminescence intensity under high excitation was observed. Utilizing the unique facilities at synchrotron, the group comprehensively investigated the energy structure and energy transfer process in double phosphates and complex oxides activated by rare earth ions. The P66 beamline, the group investigates also the exciton luminescence of perovskites, which allows a research in decay times of around 0.2 nanoseconds. Such scintillation parameters will significantly increase the resolution of positron emission tomographs. Here we thank our collaborators, the DESI and the researchers of the BLI for many years of cooperation. Also, our scientists all conduct research in the Solaris Synchrotron Center in Poland. This is X-ray photoelectron spectra, as well as total electron yield and total fluorescence yield X-ray absorption measurements. The scope of quantum research is very broad, covering fundamental and applied investigation. But most importantly, we believe that our future lies in the hands of our young scientists. Many of them have already done experiments at different European synchrotrons. For example, here are our students at the DESI summer program in Hamburg. We hope that soon we will also work on the Ukrainian Mauka beamline and at the Solaris Center in Poland, and eventually on the synchrotron built right in Ukraine. Thank you for attention.
Thank you, Oleh, for very condensed information, and it is very interesting for me to know also and about synchrotron, a special case. Maybe some questions about this. Okay, then we are in time. Thank you very much. Thank you. Now, the next speaker, now we switch to superconductivity until Sergey is changing. It is the example. If you want to switch to Mac or your own laptop, then it is possible, or we will see now whether it's possible or not. Sergey will show it. But we are switching now to superconductivity. You have noticed that this on the program that it is workshop mainly devoted to magnetism, but still there is some time for superconductivity, and now such a session.
Yes, like this. Okay, thank you very much. Thank you, Alexander. It's a very special event for me, and I'm very grateful to Jeroen, Bernd, and others who initiated the project. I'm very grateful to Ukrainians who protect our safe life in Europe. I'm grateful to all you, to young mind. So we do ARPES, meaning the main data set in ARPES is the angular distribution. So it's a very simple method. We shine photons at the surface and we analyze the electrons which escape from the surface. To define the direction in space, you need just two angles. And the angular distribution is this map as a function of intensity, as a function of these two angles. Why this is a primary data set in ARPES? Because for electrons with equal speed, this data set corresponds to the spherical section of the three-dimensional brilliant zone. So this is the only technique where we'll give you direct probing of the three-dimensional brilliant zone, and if one has a luxury to have a synchrotron, to have access to the synchrotron radiation, one can scan the whole three-dimensional brilliant zone by changing the radius of what we call emission sphere. I show you the example of these measurements we've done recently, and you see that the full three-dimensional Fermi surface can be scanned within I think 100 minutes, 100 Fermi surfaces, per one Fermi surface, 100 caught for a minute, and it allows you to see the holy grail of condensed matter physics, at least for metals, which defines probably 95% of all physical properties. Of course, photoelectrons have kinetic energies, and one could study the dependence of kinetic energy. But because the momentum of the electron, which we detect directly connected to this kinetic energy. One is not able to see the intensity from the binding energy and momentum simultaneously, because this axis is also a momentum. This axis is also momentum. That's why as soon as kinetic energy changes, momentum also changes, and we deal with a very difficult projection from the full-dimensional data set. That's why we prefer to stay close to the Fermi level. Anyway, again, as these electrons define most of the physical properties, this is the idea. Then this approximation that one could consider this as a binding energy still holds. So that's why if one concentrates close to the Fermi level, one can one can study the whole three-dimensional Brillouin zone also in terms of momentum and energy. In order to study such electrons, we need very special equipment. And here we have perhaps the largest in the world ARPES station, which is installed at BESI. And all our setups in order to study these elite electrons have extremely low temperatures. The base temperature here is below 1 Kelvin. And this allows us to study those electrons with very high precision, because the Fermi function, the temperature broadening usually smears out the details. So this allows us to do it with a very high precision. And this is perhaps the smallest ARPES system in the world. This kind of setup, it's pretty much similar to tomography in medicine. And this one is we call it microscope, because here we could study the electronic structure with the highest possible nowadays precision. And this one is like an instant camera, which allows us to see the pictures of the Fermi surface instantly on the screen. With the later, we also can observe very large portions of Brillouin zone. So here is a picture of Lviv from above if you use the so-called fisheye lens, so one could really see more. This is in the same analogy. We could accelerate photoelectrons and one could see the pretty big portion of the Fermi surface of this material, for instance. And if one compares the synchrotron-based data at 100 TeV, so this is now possible in the lab. Still another example of these studies. With this new equipment, one is able to study very different materials. And I'm proud to show you that one of these systems will come to Ukraine right after the victory. This is already prepared. This delivers the data. This is the system which is made, which is constructed and functioning due to the project which Alexander mentioned in the beginning. And it will be transferred to Kyiv Academic University as soon as possible. Good. So the next object in my title is platinum bismuth tube. This is extremely interesting material. If you take bismuth platinum atoms and consider simple triangular lattices and put them together, you will already have a very good approximation of its crystal structure. In reality, bismuth atoms are a little bit larger than the platinum ones, and this kind of lattice realizes only if one dilutes the bismuth 1 out of 50 atoms, if it's replaced by the smaller tellurium. Indeed, this kind of layers of triangular lattice realized in nature. If we want to keep the material stoichiometric, the bismuth atoms are, as I said, a bit larger, so one of them goes away from the plane, goes out of the plane, and this brings some distortion of these layers too. That's why this material becomes non-centrosymmetric. It has two terminations, this kind of kagome-like and decorated honeycomb, and exactly this material is very exotic physical properties. So the crystal structure can be understood in these terms. It turned out that it's not trivial to distinguish these kind of structures using the conventional diffraction methods. And here, again, our instant camera equipment allows us to solve this problem almost instantly within an hour or so. So one could see that doing ARPES on these surfaces, one could see that they are the same, and doesn't matter how we cleave it. And from this material, from the stoichiometric platinum bismuth 2, one can clearly distinguish the surface, which is kagome-like or decorated honeycomb. So this is example how one can use the ARPES in the laboratory also for characterization of a single crystal. Another peculiarity of the material is that whenever you cleave the material, it always exposes either one surface or the other surface, depending how you glue the crystal. So you can basically mark the simple holders with a kagome type or decorated honeycomb. This very unique property, which implies kind of absence of the stacking folds. Bend structure is pretty complicated. It's pretty complicated. There are 5 to 6 zones depending on who does the calculations crossing the Fermi level. You see the substantial contribution of three-dimensionality, and this is exactly the task for the ARPES and for all our possibilities with ARPES, which I mentioned in the beginning. So here, one remark that if you do DFT, if you compare, and this is what you find in 95% of the papers, if you compare the Fermi surface with a constant cut at KZ, you'll never get perfect agreement with ARPES, also because you have to consider the emission sphere. So here is, again, data taken at the synchrotron, and if you consider constant cut of the Fermi surface, there is hardly any agreement that you cannot recognize the material at all. If you cut your bend structure calculations by the sphere and pick up the intensity, taking into account this effect, then you start immediately to see what's going on. The same holds for the energy dependence. So if you do DFT, it's very nice to have the comparison with ARPES block, which is very easily programmable. And we did it also with the help of Ukrainian students. This is our brute force approach for platinum bismuth 2. As I said, we scan the three-dimensional Brillouin zone by cutting this by a different emission sphere, radius of emission sphere. We found pretty good agreement with bend structure calculations, and the main purpose was to establish the electronic structure along KZ so that we can navigate through the three-dimensional space. The main result of these measurements was to find the photon energies which correspond to the high symmetry direction point along the KZ direction. There is a reasonable agreement with theory, but okay, so this is another material where the bend structure can be nicely measured by ARPES. And this long time, this material remained to be like this. We started it also a long time ago. Temperature of this measurement, this was, I think, 1 squared, which is slightly higher temperature, like 10 kelvins or so. Fermi arc. The interesting thing started after our colleagues from Jeroen's institute realized that this material is a wild semimetal. Wild semimetal probably does not need to be introduced. This paper is cited probably more like 6,000 times by now. And as the topological surface state of the wild semimetal, there you can draw, for the students, you can draw a parallel. It's like topological states are at the boundary of a nice single crystal three-dimensional bend structure and vacuum, pretty much nothing. It's like Ukraine is protecting nice life. The boundary, it is protected, and it is protecting with what, with what. So these topological Fermi arcs are protected states of the wild semimetals of the three-dimensional bend structure. And after our colleagues saw this, detected these wild points, the natural question comes is, how about these Fermi arcs? They did very nice calculations showing that the different terminations show different kind of the Fermi arcs, and knowing, so guided by theory, we know where to search for those states. And our first measurements indeed indicated that these kind of points nicely agree with the Fermi arcs calculated in theoretically. It's also termination dependent, but now we knew where to look for them, and you can see them even at different photon energies. So for instance, here, they're schematically represented by these red arcs. You can, if you look closely, you can find them on the Fermi surface maps. And this has been overlooked earlier. Also in the energy dependent, we started to see some spots of intensity which nicely corresponded to the theoretical calculations which take into account the surface states. The next step was to apply our microscope to see those states with the highest possible resolution. And our first attempt indeed showed a very unusual feature, this kind of point on the screen. And to give you an idea, what we saw is that the usual bulk state, this is a red energy distribution curve, which is already, these data were quite good because we saw dispersion, and laser ARPES is quite demanding techniques. We were happy to see this, but these spots is like when you go through them with the energy distribution, you see that this signal to noise ratio could reach 50, and this was very unusual. And we understood that what we see is a record thing, is very narrow features, never seen in photoemission earlier, and they are attributable to those Fermi arcs. Superconductivity. Yeah, superconductivity. When one sees in photoemission extremely sharp peak, then and we studied a lot of superconductors before, and one immediately suspects, oh, maybe it's something to do with superconductivity because there is a coherence, the coherence peak, or something which is a hallmark of superconductivity. Indeed, when we heated up the sample, these features almost, this sharpness disappeared, and we started to investigate the temperature dependence and the characteristic behavior of the dispersion in the superconducting state. If we consider BCS opening of the superconducting gap, in ARPES, one doesn't see an occupied part, but one could follow the position of the peak and position of the leading edge, peak in the derivative. So these are the results for the arcs on the Platon bismuth 2, and we see that indeed there is a bending back of this dispersion, like in the opening of this classical superconducting gap. This has been done for different samples, and it was extracted from peak position and from the leading edge position. Temperature dependence, detailed temperature dependent. I show you the recent data, not published yet, shows very classical behavior with superconductor. So above TC, you have a rather incoherent broad peak. As the temperature decreases, you see the shift of the leading edge and shift of the peak. And if you track the leading edge, for instance, you see rather a strong, well-pronounced transition at that rather unusual temperatures, about 20 kelvins. If we have superconductor on the Fermi arcs, which are non-spin degenerate states, then one starts to suspect, oh, maybe there is a topological superconductivity there. So this is another level of protection, right? So we have conductor, you have insulator, and you have a surface states as a protecting states. You have wild semi-metal as a border case. But in this case, we are considering the superconductivity at those topological surface states. They are non-spin degenerate. So we thought, oh, maybe they could have something to do with topological superconductivity. But it turned out, for my naive experimental understanding, was every superconductivity on topological state is topological, but this was not the case. And again, with help of Jeroen's institute groups, we considered this question more carefully. We increased the precision, so now the precision is very high. So you can compare the synchrotron data. You see all the gray broad features is bulk background, and the arcs can be seen now very sharply, even at the synchrotron, even at relatively high energies. Again, they are very different, so you cannot mix up the terminations. And in terms of laser, we increased the precision also in the laboratory. So now the arc, this is the only arc. So if you do instant camera image, you see this kind of fuzzy picture, and the arc is here. But if you do it with a laser, with a microscope, which we call microscope, with a very high precision, you see unique things. These are raw data, and the arc is so pronouncedly seen, also its dispersion. And these are the record sharp momentum and energy distribution curve. Reciprocal angstrom means this is already thousands of brillons on size. So having this precision, we looked at how the gap behaves on the arc, since the arcs can be resolved with such precision. So we went along the arc, and we have found out that the gap is anisotropic. And as our theory colleagues actually pointed out before us, they said, oh, look, this is a node. And indeed, so we double checked. The gap was absent at the nodal direction. And having this anisotropic gap, one starts immediately thinking about the unconventional superconductivity. We have studied BISCO earlier, and we have something with which to compare. We did try different methods how to extract this, because the behavior of the back gap close to the node is influenced by the temperature, by the Fermi function. So we applied different methods following also the trailing edge. And if we compare to the BISCO, we realize that actually how nodal is nodal. It's actually more nodal than in BISCO. So there is, from experimental point of view, there is no doubt that this material has a V-shaped nodal superconducting gap. We can directly compare now the arcs, the map of the arc in platinum bismuth 2 with the arc in BISCO. Even visually they see similar. Okay, these are slightly different momentum scales, but nevertheless, so it's also visually looks like BISCO, and now we could study BISCO with, again, unprecedented precision. This kind of width is at least twice less than any published EDC on BISCO until today, with any equipment, with any group. Fine. This is my naive experimental understanding of what's going on. This is Majorana cone. And after discussion with the theory guys, I came and tried to understand it. And then I sent it to Jeroen. He confirmed, yeah, this is sort of things, this is correct. So I'm showing to you, if you cut this kind of electronic structure, and so here you can follow, this would be the gap function. This is the BCS-like dispersion. This is nodal direction where the gap is 0. What it means that we have a unique topological system which bears all signatures of a topological superconductivity. Indeed, they calculated, now I come to the I wave, they calculated the symmetry properties of what, they analyzed what could be symmetry properties of this kind of superconducting gap, which is repeating 6 times in the Brillouin zone. And the symmetry analysis showed that it doesn't correspond to the A1, and this agrees with the A2 irreducible representation, and the function with the lowest L value, which describes the behavior of the nodal gaps on all these 6 arcs, is indeed L equals 6, which means this is I wave. So there's no marketing here, but this came out purely out of physics, out of theory, and symmetry considerations. And yeah, so this is the reason for my title picture. They did very nice calculations of how would the superconducting gap behave if when one considers different coupling potentials. Here is a simplified model which showed that indeed considering the superconducting gap opening on the Fermi arcs, one would see the Majorana state, which would be located on the hinge states of the crystal, and this is the probability to find them. So in principle, translating to the modern language, which you could see even in the media, this could be good for quantum computing, but with this particular material, there was still room for improvement, but nevertheless, this is exactly the states one is looking for to apply to the quantum computing, because they are protected. What next? Do I have a couple of minutes? Yeah, good. What next? We are still working on this material, and now the arc, experimental arc, and this is a theoretical arc, experimental arc and theoretical arc, they really approach each other. We could study by tunneling the same surfaces of the crystal. The Fermi surfaces become sharper and sharper, and we started to look at the agreement between the theory and experiment in terms of dispersion. And it turned out that on one of the surfaces, the dispersion is actually one-to-one correspondence. So this is decorated honeycomb. You see, this is the same energy scale, the same momentum scale. This is what theory predicts. This is what we measure in experiment. So basically one-to-one. If you look at the other surface where we saw the I wave superconductivity, this is the theoretical dispersion, and this is experimental observation. So these are different directions. So we cut the arc perpendicular and along the nodal direction. Especially interesting is this thing. So you see, instead of the parabolic dispersion, like here, so this was reproducible here, we start to see something strange here. So it's evidence. Typically, this is evidence for the strong coupling. I'll come to this later. One-Hopf singularity is another requisite of a high-temperature superconductivity, and it looks like we have it also in the arc states. So theoretically, the saddle point is seen here, and we confirmed it experimentally. One could go along this direction and see the hole-like dispersion, and one could go perpendicular and see the electron-like dispersion. This is evidence for the one-Hopf singularity, which is present at this Kagome-type surface. So theoretically, the one-Hopf singularity saddle point in 2 dimensions is much stronger than in 3 dimensions. That's why these peaks in density of states are very favorable for the superconductivity. The other surface, as I said, this one, is extremely interesting in terms of the strong coupling. We tried to analyze it in terms of self-energy, and we realized that there is even divergence. So the coupling is so strong that these 2 branches of dispersions are kind of teared apart by this strong interaction. This is a 3-dimensional representation which shows how the usual parabolic type of dispersion is distorted by this strong coupling. So this could indicate, could give a hint what is responsible for this superconductivity. Finally, we realized that the size of the arc can be different if one goes through the crystal surface. If one scans the surface, the size of the arc is different, but it also means that the underlying dispersion is tunable, meaning that we are dreaming that one could tune this one-Hopf singularity closer to the Fermi level. We cannot control this effect, but this is probably what is responsible for the large gaps observed by tunneling spectroscopy. So this is this is a work in progress. We try to learn how to control these things. So we believe it is very promising. At this point, I will stop. I'll show you the conclusions, and so I showed you what is ARPES, what we mean by ARPES. I showed you that platinum bismuth 2 is a Wilson metal with localized arcs, localized in terms of energy, in terms of K, in terms of space, and in terms of spin. So this is really a unique object. They be a topological high-wave superconductivity, and the arc states are potentially tunable, and be all signatures of the objects which are good for the high-temperature superconductivity. And the last but not least, I would like to thank all my collaborators. So here you will find the people from my group in Dresden, the crystal growers, the Ukrainian colleagues, Jeroen's team, Bessie people, also theorists from other institutions. And again, I show Jeroen and Bernd, who are the great supporters of Ukraine and who make this kind of meetings possible. So thank you for your attention.
Thank you, Sergey. We still have a possibility, of course, for a few questions.
Thank you for a great talk. Yes, we have microphone for questions.
Yeah, maybe
microphone. Yes, again, thank you for a great talk and really impressive experiments. So my question is really about interpretation, because if you look at your modeling of your superconducting order parameters, sine L5, which has no. If you're trying to compute the topological invariance for that gap, you actually get something which is non-zero.
Jeroen? Sorry. Topological invariance for the gap, you're saying?
Yeah, because you need D vector in the Bovhyra, which has 3 components, otherwise you don't get it.
But you do get for sure a Majorana cone that has a term number associated to it. So that is topological. But what you're asking now is the D vector. You want to have a model.
The D vector for the D Hamiltonian of the superconducting.
Yeah, so that's you should look into that, but that should reflect in the topological invariant related to the D vector. I don't know.
It's not a fully gapped state, so then it's not it's not a fully gapped state, so then it's not the winding number of the D vector.
It's not the winding of the D vector, but it's a property of the D vector somehow.
Now, this is what I wanted to say.
More questions? I was thinking this interaction, the last slides about strong interaction, could they be described within the self energy, or it is just organization and it is a gap?
The problem is that theoretically there is only one single parabolic dispersion gap. So the interpretation is kind of inevitably leads to the coupling to something else. And this something else in the calculation, we cannot identify. So one could do it in a kind of the real part of a self-energy. You see the upper branch, lower branch here. So you could identify perhaps the energy of this something.
So you don't see any backfolding dispersion, like the gap open between Borisenko?
No. There is no evidence. There is no requisites for charge density waves or whatever. There is no any kind of surface reconstruction. So with this kind of precision, we can exclude this. This is the very remarkable effect to my taste.
Okay.
It's to be understood.
More questions? Yeah. Oleh, please. So the potentials.
Well, this is the IFW code mostly, and they use the Vanier approach for calculating the surface states. But the band structure can be also calculated by, we had also calculations from Stuttgart, and the results are in agreement. Of course, the surface calculations are always the highest quality from Jeroen Institute.
Of course.
Yes.
Okay. Thank you, Sergey. So we should move. And the next speaker, Kristian Mæland. Do you have a presentation?
Yeah,
here? It's already here. It's in here. Okay. It's in here. No problem.
Okay, so we're back on Zoom. So I think just to recap, we have the Fermi arcs. You already saw them in the last talk. So recent experiments have seen a dominating surface superconductivity in this material. So an example is the ARPES measurements. So they measure the Fermi arc bands and see gaps opening around 10 Kelvin. At the same time, the bulk states remain metallic. Also, STM measurements see gaps opening on the surface. The motivation of our work is to find a candidate mechanism for this highly unconventional superconductivity. This could be an intrinsic realization of topological superconductivity, and there's signs that it's a high angular momentum I-wave superconductor. So we base our study on an effective model of a wild semimetal designed to capture the main properties of platinum bismuth 2. So the effective model replaces the complicated lattice structure by an hexagonal crystal with a single atom in the unit cell. There are 2 orbitals per site, and importantly, the effective model has the same symmetries as the material. The Hamiltonian also contains spin-orbit coupling and a term that breaks inversion symmetry. For the bulk, this is a 4-band model of a wild semimetal, and like the material, it has 12 Weil nodes. So in such an effective model, the density of states at the Fermi level in the bulk is extremely small, even with some small tuning away from the Weil nodes. So from the point of view of effective models, the reason surface superconductivity dominates is just that the density of states there is higher. So here I show you the band structure in a slab geometry. So here the bands are colored by the location of the eigenstates along the z direction. Between gamma and m, you can see surface states from top surface and bottom surface crossing the Fermi level. Figure C shows the full Fermi surface. Again, with the colors, you can see how parts of it are the Fermi arcs on the bottom surface, parts of it are Fermi arcs on the top surface, and parts of it are more bulk-like. So that's the projection of the bulk Fermi surface. So like the material, we place the Fermi level slightly below the Weil nodes. That's also why the Fermi arcs appear at different K for the different surfaces. Also note that the electronic states are most surface localized in the center of the Fermi arc. So we thought phonons were a natural starting point when looking for a mechanism in this material. There are no indications of strong correlations in platinum bismuth 2. So we derived the phonon spectrum by using a force constant approach. So we consider the same crystal and assume the same symmetries as in the electron model. For the bulk, this gives us 3 acoustic phonon modes. Those are the dashed colored lines in the figure. In the slab geometry, there is instead 3 times the number of layers different phonon modes. So those are the black lines in the figure. So 3 of those are still acoustic, so they have 0 energy at the gamma point. But the rest are optical in the sense that they have a non-zero energy at 0 in-plane momentum. We then derive the electron-phonon coupling by Taylor expanding the hopping terms around small ionic displacements. So this gives us an ionic displacement multiplied by an electron hopping. If you then quantize the displacement as a phonon operator, you have a model for your electron-phonon coupling. The phonon-mediated electron-electron interaction now involves a sum over all of the phonon modes in the slab geometry. So we work in the band basis, so we consider Cooper pairing out of the long-lived fermionic excitations on the surface. And so this interaction also contains the electronic eigenstates from this transformation. Unlike the usual case for phonons, we find that this interaction can be peaked at 0 momentum transfer. So in terms of real space, it's as if the phonon-mediated attraction is long-ranged on the surface. And this is due to terms arising from the out-of-plane hopping. In simplified notation, the electron interaction looks like this. So we have the strength of the electron-phonon coupling, the G factor squared, divided by the phonon energy omega. So usually for phonons, this G factor goes to 0 when K prime is equal to K, but that's not the case for the out-of-plane terms. In the slab, there are phonon modes with a very small non-zero energy at 0 momentum. So you can see how this can make a significant contribution to the interaction. So with more details, the G factor looks like this. So here you have orbital indices L, you have the layer index C, you have the C component of the nearest neighbor vector delta and the phonon mode M. All of this has to be summed over. The important part is inside of these square brackets. So these E vectors here, these are the phonon eigenstates. Usually the phonon eigenstate just goes outside, and this G factor goes to 0 if K is equal to K prime. Here, okay, yes. So this figure shows you the solution of the linearized gap equation on the Fermi arcs. So figure A shows the real part. The gap is positive for positive Kx, negative for negative Kx. This is a Px wave gap. Figure B shows the imaginary part. It's also non-zero. It's Py wave. So here we effectively have a spinless chiral P wave superconductor. And that's a prime example of a 2D topological superconductor. Figure C shows the absolute value of the gap. It's the same on all of the Fermi arcs. And this is a fully gapped state. In fact, this state is an intrinsic realization of the Fu and Kane model. So they imagined interfacing a conventional superconductor with a topological insulator. In that case, the chirality of the surface state turns the S wave gap into a spinless chiral P wave gap. So such extrinsic methods involving conventional superconductors remain the most common in attempts to realize Majorana bound states. But intrinsic realizations are highly attractive. It could offer higher critical temperature and so larger gap amplitudes and more stable future technological devices. So what we see here is that phonons alone can generate topological superconductivity on the surface of wild semimetals. So it only relies on the lattice vibration of the material itself. So in this situation, you can think of the phonons as providing an S-wave pairing, and then the chirality of the Fermi arcs turns this into spinless chiral P wave. So in ARPES, they can measure the absolute value of the superconducting gap, and they have now been able to do that in platinum bismuth 2 as a function of momentum along the Fermi arcs, as we saw in the last talk. So here the blue curve is a schematic of the experimental result, and it indicates a node of the gap in the center of the Fermi arc. So that's a highly surprising result if surface superconductivity dominates, then why is the gap 0 where the electronic states are most surface localized? The orange curve is the theoretical prediction from phonons with a maximum gap in the center of the arc. So this fully gapped topological state could be realized in other wild semi-metals, but we wanted to see if we could find a mechanism that can explain this nodal state. So a hint for this is that in the center of the arc, the electronic states are most surface localized, so they're most compressed in real space. And that should also then mean that the Coulomb repulsion is strongest in the center of the Fermi arc. And indeed, we find that by combining phonon attraction and Coulomb repulsion, we can explain the nodal state in a situation relevant to platinum bismuth 2. So first, let's repeat this experimental result. So in ARPES, they see the Fermi arc bands. At a low temperature, they see the band bending away from the Fermi level and can estimate the size of the superconducting gap. So from figure B, there is an experimental uncertainty in the absolute value, but the most likely explanation for this is a sign-changing gap function. So by a symmetry analysis, they identified it as I wave. So that's a high angular momentum function. If you follow it on a circle around the gamma point, there are 12 nodes. So 6 nodes in the center of each of the Fermi arcs, and an additional 6 nodes between the Fermi arcs. But I wave is even in momentum, and I just told you that the gap in the band basis has to be odd in momentum. But this is not a strong contradiction. In the symmetry analysis, they moved an odd parity factor from the electron eigenstates into the number spinor. That factor turns out to be chiral p wave that comes from the spin-orbit coupling in the normal state, and it represents the chirality of the Fermi arcs. So here I show for a circular Fermi surface the result of multiplying I wave by chiral p wave to get an odd parity gap in the band basis. We then get an unusual complex combination of H waves. So H wave typically has 10 nodes on a circle around the gamma point. Here, each of them have an additional 2 non-sign changing nodes. And the nodes of the real and imaginary part line up, so that when you take the absolute value is just like an I wave. And you can see that in the equation that this e to the I phi k factor can change the absolute value of the gap. So it's essentially a matter of choice if we call this an I wave or an unusual complex H wave. In my case, I am looking for an the odd parity version of the gap. So for this value figure, the background in gray schematically indicates the location of the Fermi arcs. So the conventional wisdom due to Morel and Anderson is that Coulomb repulsion does not have a big effect on phonon-mediated superconductors. So that's most easy to understand for S-wave superconductors. So for the moment, imagine a normal metal. So here I show the BCS gap equation. We have the gap delta, we have our interaction VKK prime, and epsilon k is the normal state dispersion. So for a normal metal, it makes sense to insert some approximations on the momentum dependence of our interaction. So we know we have a phonon-mediated attraction that's mainly active close to the Fermi level up to the maximum phonon energy, the Debye frequency omega d. There's also a Coulomb repulsion that's active in the entire electron bandwidth up to W. So here the small u is the phonon attraction, the small v is the Coulomb repulsion, and they are both treated as isotropic, usually a good approximation in normal metals. It then makes sense to insert a similar approximation for the gap. So it takes one constant value delta 1 close to the Fermi level and another constant value delta 2 farther away from the Fermi level. This is then a schematic of the solution of the gap equation, and the result is that delta 1 and delta 2 have opposite sign. So that way they are taking advantage of the Coulomb repulsion between them in the gap equation. So you see from this effect, you can even have a stronger Coulomb repulsion than the phonon attraction, and there is still a non-trivial solution to the gap equation. In fact, you can in the end write down an equation for delta 1 that looks a lot like what you have from phonons alone, just with a small quantitative correction. So that's the Morel-Anderson pseudo-potential. And this all relies on a much larger electron bandwidth than the maximum phonon energy. In our case, the relevant electron bandwidth is the bandwidth of the surface state. That's because surface states and bulk states essentially decouple due to the negligible real space overlap of their eigenstates. Also, we consider a wild semi-metal, not a normal metal, so we should expect things to be far more anisotropic. We model a statically screened Coulomb repulsion by an on-site term U and a nearest neighbor term V. We transform that into the band basis, and then we have a Coulomb interaction that has a lot of momentum dependence, but it's mainly through the electronic eigenstates, these V factors. The nearest neighbor term comes with its own inherent momentum dependence, and that makes the Coulomb repulsion even more peaked in the center of the Fermi arc. So we first looked at solving the gap equation in the full first Brion zone with the anisotropic interactions. If we first consider a case with a large surface state bandwidth, then the phonon attraction is only active in a small region close to the Fermi arcs. The Coulomb repulsion, on the other hand, is active for the entire surface state. So for such a situation with a large surface state bandwidth, we find a generalization of Morel-Anderson physics to unconventional superconductivity. So here figure A shows the energy of the surface state at all momenta where there is a surface state. The red region between gamma and M, that illustrates where the phonon attraction is active. If you follow that into figure B of the real part of the gap, you see a px wave gap, just like we had before from phonons alone. So that's like a generalization of delta 1 to a momentum-dependent gap. If you go radially out of that region, the gap changes sign, and that's a generalization of the delta 2 equal to minus delta 1. So in the end, this is just quantitative corrections to what we had from phonons alone. But we realized that there is a way for the Coulomb repulsion to have a qualitative effect, so to change the preferred gap symmetry of the gap function. And the key is to reduce the surface state bandwidth. If you look at figure A and imagine reducing the bandwidth of the surface state, the red region grows in size, and eventually this radial sign change of the gap just stops being effective. So we don't need the exact limit of equal bandwidths, but that's the simplest case. Let's consider that for simplicity. So here I show you new figures at new parameters. Here the surface state bandwidth is approximately equal to the maximum phonon energy. And I stress that this is relevant for platinum bismuth too. So they have measured the Fermi arc bands and they have measured the phonon spectrum, and both appear to have a bandwidth around 20 MeV. For such a situation, we can solve a linearized Fermi surface averaged gap equation. So it's shown on the top here, we have the dimensionless coupling lambda, the gap delta as a function of momentum parallel to the Fermi surface, nk is a momentum-dependent density of states factor, and vk prime is our interaction. So that's now a direct sum of phonon attraction and Coulomb repulsion, because both of them are now active in the entire energy range of the surface state. The figure then shows you the dimensionless coupling as a function of on-site repulsion U and nearest neighbor repulsion V. Different colors indicate different preferred gap symmetries. Most importantly, the purple region, that's the I wave state with a node of the gap in the center of the Fermi arc. And that ends up dominating the parameter space. We can understand that by considering what these different gap symmetries mean in terms of real space Cooper pairing. So the orange region at weak Coulomb, that's the chiral p-wave gap we had from phonons. So that's in the band basis. We can transform it into the spin basis and look at the singlet triplet mixing. So there's a mixing of S-wave singlet and P-wave triplets. So this can be represented as both on-site and nearest neighbor Cooper pairing in real space. And therefore its dimensionless coupling lambda decreases both with U and with V. The gray region is closely related to the orange ones. There's just some accidental nodes. The blue and green regions, these are higher angular momentum fully gapped states. So chiral F wave, chiral H wave. They do not have any on-site Cooper pairing in real space. So their lambda is independent of U, but they do have nearest neighbor Cooper pairing in real space. So their lambda decreases by increasing the nearest neighbor Coulomb repulsion. In the orange region, you can see in the purple region, you can see that lambda is independent of both U and V. So the I wave state has such a high angular momentum that the real space Cooper pairing is longer ranged than the screened Coulomb repulsion. And that's why it ends up dominating the parameter space. So essentially in this small electron bandwidth situation, the role of Coulomb is to gradually increase the angular momentum of the preferred gap function. It is then essential that the phonon-mediated attraction has a long-ranged component that can support the high angular momentum pairing. So here I show you the solution of the gap equation in the purple region. And you see that we indeed find this unusual complex combination of H waves. The absolute value of the gap has nodes in the center of all of the Fermi arcs, just like the experiment on platinum bismuth 2. And as we heard, this is also topological superconductivity. So it's not a fully gapped state, but since we have a non-degenerate Fermi surface, nodes of the gap are Majorana fermions. That's due to the particle-hole symmetry of superconductors. That can lead to Majorana zero bands on the edges. So in this case, the edges of the 2D surface. So here I show you the BCS prediction of the critical temperature Tc. It's not always the most reliable, but what should always be true is that if you have a larger dimensionless coupling lambda, you will also have a larger critical temperature. So one prediction from our results and our proposed mechanism is that if you can somehow better screen the Coulomb repulsion, then the critical temperature should increase and the gap should become nodeless. So also if the critical temperature increases, the gap amplitude increases at low temperatures. So one proposed way of tuning the screening of Coulomb is through Coulomb engineering. So you bring some other material with a high dielectric constant close to our wanted material. So you can think of this blue slab as the bottom surface of the vial semi-metal. Alternatively, tuning the density of states can affect the Coulomb screening. And as we heard, there's experimental indications of a Van Hove singularity close to the Fermi level. So maybe small details in the cleaving change how close to the Fermi level this Van Hove singularity is. That could affect the screening. So I can speculate that that could be one possible explanation why different experiments see different gap amplitudes. So we found that the phonon-mediated electron attraction has a long-range component on the surface of vial semimetals. In that case, if you have comparable electron and phonon bandwidths, Coulomb repulsion can lead to nodal gaps. And that can explain the nodal topological superconductivity observed in platinum bismuth 2. So thank you.
Thank you. Could be in time, despite of this technical problems. Questions, please. Does anyone have a question? So maybe naive question from me is, you show us that it is possible to explain this nodes with phonon mechanism of pairing. In cuprates and in iron-based superconductors, just the appearance of sign-changing gap was the solid argument about spin fluctuation scenario. Is it considered here? Or?
Yeah, so I would say that's this step where I go through the Morel-Anderson physics. So the Morel-Anderson physics is basically the good argument why phonons only give you S-wave and nothing changes. So it's really key here, I think, that the electron bandwidth is also small. And that way you get around the Morel-Anderson physics. And then if you have anisotropic electron-phonon coupling and anisotropic Coulomb repulsion, you can have non-trivial solutions to the gap equation that are not necessarily S-wave, but it can be higher angular momentum.
Yeah, I understand. I mean, whether the spin fluctuation scenario are also considered.
Okay, yeah, people. Yeah. So in this material, you mean? So we didn't consider it, and so far no one has. And I think the argument is that according to the experiments, there's no indications of strong correlations. So the ARPES spectra fit very well with the DFT. I think the small exception is this one surface state, but like the bulk states perfectly match almost.
Okay.
So I have a question. Thank you for the very clear talk. Can one distinguish the I wave with this modified H wave? Well, not from the ARPES, right? But if you would do some kind of interference experiments or possibly in the vortex responses, do you expect differences there?
Yeah, in principle, but my opinion is that we're talking about the same superconducting state. So this all has to do with the electronic eigenstate in the normal state. So as long as the Fermi arcs actually are non-degenerate states with a spin momentum locking, it is this complex H wave. So if you call it an I wave, you've just moved the chiral P wave into your number spinor.
Okay, so
yeah, so kind of
it's a nomenclature thing.
Yeah.
The physical response is the same.
Yeah,
right?
so everything is somehow hidden away in the eigenstate, and I guess in these things you are thinking about, the eigenstates of the superconducting state will determine what you're measuring. And I think we would both describe the same thing.
Okay.
Yeah.
More questions? Sergey?
That's very nice talk. From the point of view of ARPES, what can we do? Would, for instance, the plane with the bandwidth give additional information if you know how to control it?
Yeah, so if the surface state bandwidth becomes much larger than the maximum phonon energy, our prediction is that you would get this fully gapped state that's more like the Foucault chiral P wave. Yeah.
And if it gets smaller,
I think for this theory, the smaller the better. That's a higher density of states, and it doesn't hurt if the electron bandwidth is smaller than the phonons. The key is that it can't be way larger.
Do you expect that the gap can be different on different? The value of the gap can be different, like in your pictures, on different arcs.
So, in principle, yes, but the experiment said that it's the same on all of the arcs. So we mostly chose that, and for the I wave, it will by symmetry be the same on all of the arcs. But in this green and blue region, there's like you can choose. Here we have two degenerate solutions, so you can choose versions that have, for instance, a node only on 2 of the arcs. But if you choose the version of this linear combination of the 2 potential solutions that's fully gapped, then it's the same on all of the arcs, and that should be energetically preferred.
Does experiment say that it is the same on all the arcs?
on one of the surfaces. The other surface, we are still working. The amplitudes are smaller, and the anisotropy is slightly different, but this needs to be understood.
I believe experiment, but I don't, the statement that it's the same on all the 6 arcs is an inference. It's not an experimental evidence. I would say you will have, if it's different on different arcs, if their symmetry is broken, then probably or possibly you will average over different domains in the ARPES, and you would still see the same thing at all the arcs. So it's it's something to be.
Just if in the summa map it looks like the same intensity, then it is easy to expect that they are the same.
Experiment.
Indirectly, we see that the arc look visually, but in order to extract the momentum dependence of the gap, this is
Much
full
more tricky.
cliff. This is really, we have to focus on once. We cannot simultaneously measure the gap with the same precision. But purely visually, we can see that there's not much difference. Of course, it needs to be proved.
Okay, no more question. Then thank you all the speakers of the session. A challenge to find a coffee break and go back in 20 minutes, let's say.
Okay. Hope everybody can hear me also online. Volodymyr, do you hear me?
Yes, I can hear you.
Okay, good. So you'll be one of the next speakers, so that's good. We hear you too. So the next session is basically magnetism, magnetic domain walls, and topological effects in magnets. And the first speaker is Dennis Sheka. Please, Dennis.
Thank you. Dear colleagues, I greet all of you. Thank you very much for organizers, not only for making me here, but also for organizing this great workshop here. Today we already had several very nice talk about topological superconductivity, and I will try to draw your attention to another topic which also connected with topological effects. Namely, we will consider curvilinear magnetism. I hope that during the talk we will see how appear new effects in new unconventional effects in conventional magnets due to tailoring geometrical factors like bending, twisting, and some manipulation tailoring of the cross section. And part of this effect are topological, part are chiral. Okay, I will present results which were obtained by our written team, and most of them are obtained by a new cohort of young students from Kyiv University, Dmitry Karakuts, Roman Sichenko, Solomia Sinyukhina. I will also present results which were obtained in close collaboration with two German teams. So I think Jeroen van den Brink, Svetlana Kondovich, Volodymyr Kravchuk, and Kostyantin Yershov from Institute of Solid-State Physics, Dresden, and also thanked Denis Makarov and Alexander Perepolsky from Helmholtz Center, Dresden-Rossendorf. First, I make a quick look on the history, very brief history of curvilinear magnetism. Here, it's nice graph from the recent review article, and in the top part you will see the theoretical progress in this field, and in the bottom part you see experimental results. So while you see that the story here starts in 1950s, so the new era of curvilinear magnetism started in this century, and probably the turning point was 2008, when Stuart Parkin invented the three-dimensional racetrack memory, which make a bridge over the gap between the theory and the real-world application. And probably the first theory of the curvilinear magnetism appeared in 2014, when they appear a theoretical framework to describe curved nanoshells. A year later, they appear a theory to describe curved nanowires. And in 2020, they appear a theory which combined both local and non-local interactions. So, of course, all the theory were possible and complemented by experiments. And concerning the modern experiments in this field, I can say that probably most of experiments are about different ways on three-dimensional nanoprinting, which includes multi-photon lithography and also focused electron beam induced deposition named as FEBIT. If we speak about evolution of materials, so it started with conventional ferromagnets. In 2020, they appear curved anti-ferromagnets. In just 2 years ago, they appear magnetoelectrics, and probably 1 year ago, they appear curved altermagnets. And today, one of the next talk will be done by Kostyantin Yershov, who will dive deeper in the curved altermagnets. Let me start with the interplay between the geometry, interaction, and new effects which appear in curved magnets. So if we speak about local geometrical properties, so we can speak about bending, which is connected to the curvature twisting of theta, which is connected with the torsion. And as a result, they appear imagined interactions, so effective anisotropy and effective Dioshensky-Marie interaction. And in turn, produce different new effects, mainly geometrical magnetochiral effects. If we speak about global geometrical properties like topology, it also results in emergent interaction, this time non-local, driven by magnetostatics, and it also produces some now non-local geometrical magnetochiral effects and topological particles. And today we will introduce new player. It's a modulation of the structure, so produced by the tailoring of the cross section, which also is very important and produce emergent interaction. We will see how it produces emergent interaction, and also results in geometrical magnetochiral effects, local and non-local, and also in topological particles. So just to short motivation, so why it is interesting. So I say that first of all, it was motivated by experimental works. And if we speak about curved nanowires, so the technology to produce these nanowires is 3D printing using Fabit. It's typically it's produced high gradients of the cross section. So cross section vary very huge, and according to experimental results, it is important to get new effects. And if we speak about curved nanofilms, different cap structures, you also see that the thickness in experiments vary strongly, and it's important to get an to make an explanation of these results. And to the date of these experiments, so there was no theory which which can explain these results. So the typical theory of curvilinear magnetism, dated up to 2 years ago, it considered only a system with a constant cross section. So let me start with the model of the curved ferromagnetic nanowire. And the minimal model just includes non-homogeneous exchange interaction and anisotropy. And namely, anisotropy is a source of geometrical effects. So because the anisotropy axis is typically follows the geometry of the sample. If the anisotropy is strong enough, it dictates that the one have to consider the system in the curved curvilinear reference frame. And this is the source of new effects. So they appear emergent interactions. So this energy should be restructured following the local symmetry of the system. And they appear two emergent interactions: effective anisotropy. Its exchange contribution is bilinear with respect to the local curvature and local torsion, and effective mesoscale Gerasimchuk interaction. So the exchange contribution is linear with respect to the curvature and torsion. And what is the place of the Varian cross section of the wire? So the answer is the cross section appear exactly in these emergent interactions. And what is the consequence, we'll see in the next slide. So just to make some physical intuition about possible effects, we consider the case of very strong anisotropy. In this case, this anisotropy dictates the assumable magnetization distribution, for example, along the wire. And in this case, these two emergent interactions, so the anisotropy and the Gerasimchuk interaction, they result in effective, like Zeeman-like interaction with effective field. And this effective emergent magnetic field, you see, it depends on the gradient of the curvature. It depends on the product of the curvature and torsion. And this new player, it's a gradient of the cross section. As a consequence of this emergent field, the magnetization starts to tilt to the direction of this field. And you will see that there are three sources of these geometrical effects, the gradient today. And what are new effects of? First of all, I will mention geometrical magnetic chiral effects, which means that geometrical chirality of sample is coupled to the magnetic chirality of the texture. And there are several nice manifestations of this effect. First of all, it's pattern-induced chirality breaking, which means the violation of the chirality of magnetic texture due on the background of the chirality degenerated states. Like here, you see the two vortex state nanotubes. The second manifestation is the geometry-induced chirality breaking, which means the coupling between geometrical chirality of the substrate and magnetic chirality of the texture. Also, it's important the topological chiral coupling, which means the triple coupling between the geometrical chirality, magnetic chirality of the texture is the topological charge, like, for example, the charge of domain wall or the charge of the skyrmion or vortex texture. And also there appear non-local magnetic chiral symmetry breaking, which is caused by magnetostatics and results to the coupling between the magnetic chirality of the texture and geometrical chirality, for example, for the vortex string. We consider first this geometrical induced chirality breaking. It was a surprise that these chiral effects appear also for the non-chiral textures, like, for example, flat parabolic curve, and it determines that the preferable sign of the domain wall. And also they appear opinion of this domain wall in the place of the maximum curvature, and it was possible to quantify the effective Zaleshinsky-Maria interaction by measuring the dependent field. The dependent position is determined by the interplay between the curvature gradient, cross-section, and the cross-section gradient. So if we apply a small magnetic field on the domain wall starts to oscillate, and again the frequency of these oscillations are determined also by curvature and cross-section gradients and also second derivatives. Why it is important and how it can be used. This geometrical magnetic chiral effect, they appear in the alter motion of domain walls. So the first theoretical idea goes back to 2018, when we considered the Oleh spiral, and domain wall can efficiently moved just by the curvature gradient. So it was theoretical prediction, but later and recently it was experimentally checked in different kind of spirals, so archimedeal spirals and more complex spirals, and it was a perfect agreement between the theory and experiments. And the driving force for the domain wall is just a gradient of the curvature. If we go to the three-dimensional curves like nanohelices, the situation is more complicated. In experiments, the automotional domain was validated by, but the main source was expected to be not the this gradient of the curvature, but it was connected with the varying thickness. And to understand this result, so we started to collaborate with experimental groups and analyze the role of the varying cross-section, and found that the gradient of the cross-section is the driving force, can be the driving force together with the gradient of curvature. And even in the straight nanostripe, the gradient of the cross-section can efficiently move the domain walls like an effective field. And also the interplay was checked and produced a nice fast motion of the domain walls in the, for example, in the so-called arc curves. Nice application of this domain wall motion, in this spintronic device could be a domain wall diode. So the idea goes back to 2020. We consider the straight nanostripe with functionally graded Dzerzhinsky-Murray interaction. So which means that the parameter of Dzerzhinsky-Murray interaction varies along the stripe, and as a result, so domain walk can be efficiently moved in one direction, but it's pinned in another direction. Now we extend this idea for the case of nanostripe with Orion cross section, and so we don't need an external Dzerzhinsky-Murray interaction. So just this effective Dzerzhinsky-Murray interaction will appear from the geometrical effect, and we saw that domain walk can be efficiently moved in one direction, it pinned in another direction, and the pinning position is determined by the interplay between the cross section and the derivative of the cross section. And if the field is not strong enough to get a direct effect, domain will start to process, and the procession frequency is determined by the second derivative of the cross section. What next in this direction with the nanowires with the variable cross section? So there are a lot of modern experiments. First of all, about the domain wall motion in the curved spectronic architectures, and another examples are spin transport in three-dimensional interconnectors, and also I have to mention the curvilinear magnonics. And all these fields, for these fields, it's very important to describe, to understand the role of the curvature and the Orion cross section. So it should be done in future. Next, I would like to draw your attention to a ferromagnetic nanoshell with Orion thickness. So the idea is very similar. So we consider the model with two interactions, exchange and anisotropy. And if the nanoshell or nanofilm is curved and the anisotropy is strong enough, so it determines the direction of the preferable magnetic state. And they appear, again, imagined interactions. So effective anisotropy and effective Dzerzhinsky-Murray interactions, again, they are anisotropy is bilinear with respect to the principal curvatures, and mesoscale DMI is linear with in respect with the curvatures. The influence of the Orion cross-section of the film is that the coefficient of the anisotropy and the Dzerzhinsky-Murray interaction, they become dependent on the thickness with which now is coordinate dependent. In the case of strong anisotropy, we can similar to the one-dimensional case, we can introduce an imagined magnetic field. And this imagined magnetic field, it results in the tilt of magnetization from the anisotropy direction, which is a supermagnetization texture. And the source of these interactions are just principal curvature. So it was result obtained more than 10 years ago. But now, what is the role of the Orion cross-section? Of Orion thickness. So you see that the gradient of the thickness of the film, it's another source of this imagined field, and it results in the tilt of magnetization. So you can consider that the tilt angle is different, so one can analyze these effects. So okay, we made just the first step in the direction. So what next? So probably the most pressing challenges in this direction are following. So first, magnetic vortices and skirmions are considered in the curved system. So typically they are produced by so using some, for example, self-organizing nanospheres, and after that they deposit a magnetic film, and the thickness of magnetic field have strong gradient of thickness, and you see that one can expect different skyrmionics and vortex and other spin texture states. So another example of effect of varying thickness is a non-local magnetochiral symmetry breaking. So it was analyzed for the nanocaps of asymmetric permolar structures, and it resulted in the chiral symmetry breaking and the coupling between the chirality of the vortex and the magnetic chirality of the vortex and the geometrical chirality of the vortex string. And also, if we speak about topological chiral coupling, like this in band nanostripes or Möbius, magnetic Möbius, which was realized experimentally, again, there appear a gradient of the thickness, which is important to be considered and to be explained. And at the end of my talk, I would like to draw your attention. Oops, I'm sorry. Okay, I show the new direction. So the curved anti-ferromagnetic wires with varying cross section, and again, so the minimal model consider exchange and anisotropy. So the theory can be explained using nonlinear sigma model for the nail vector. Instead of magnetization like against ferromagnets. As a result, they appear imagined magnetic field which acts on the anti-ferromagnet. So it depends on the gradient of the curvature, gradient of the cross section, and the torsion. In this case, it's formally similar to the ferromagnetic. So the main difference appear in dynamics. So because in dynamics, anti-ferromagnets had at least two sublattices. That means they appear twice more different frequencies. And if we speak about domain wall dynamics, they appear two different frequencies, which depend in different ways on the geometrical parameters. So differently, for example, one frequency of the main position of the domain wall is named here omega q. It depends on the second derivatives of the curvature, second derivatives of the cross section, and their product. And the frequency of the face of the domain wall, it just depends on the curvature. Okay, it's just preliminary results, and I would like to show what should be the next. So where these effects are important. So first, it's in dynamics. If we speak about curvilinear anti-ferromagnetic magnonics. So the first steps were done in 2020 when we consider three-dimensional anti-ferromagnetic helix structure. And what is interesting that during the curvature, there appear a coupling and the hybridization of different branches of spin waves, and moreover, so one of the branch have a negative group velocity, which means that it could be a point for the Bose-Einstein condensation of magnets. So, and okay, it was just the first step, so it was not considered the effect of the varying thickness, so it could be also very important. So 2 years ago, there appear a new guy in this direction, so it's a curvilinear magnetoelectrics. And in these systems, they appear effects of frustration of anti-ferromagnetic domain walls and multiple ferrotoroidal response in this system. So, and the last example concerning films with varying thickness. So we considered anti-ferromagnetic domain walls in chromium systems with some topographic features, so domain walls can be efficiently tailored by these mesostructures, and it can be used for some future anti-ferromagnet memory devices. So just to conclude, I would like to say that this mutual interplay between geometry, topology, and this imagined effect, it's very important, and one can efficiently manipulate by different topological and chiral effects with conventional magnets just by bending, twisting, and tailoring the cross-section. And I hope that the synergy between this phenomena, material science, and possible application will give push to new ideas and new application. So thank you for your attention.
And thank you for your talk. If I may start with the question. So it's always that the gradient of the thickness enters multiplied by either the curvature or the torsion, right?
And not always.
So then you have to explain.
Yeah,
that.
yeah. Mm-hmm. So, yeah, in fact, so when the first experiments appear, so it was an idea, so it's appeared together, but finally we, as usual, we start with a complex system. After that, we simplify it. And we realize that even in a straight wire, so there is a response just by the gradient of the cross-section. But of course, if we consider the curve system, there appear some terms which depend both on the curvature and the.
But they cannot give rise to a tilting, right? If there's no curvature, then it will not give rise to a tilt. Or does it?
No, it does. It does work here. Yeah.
Okay.
Yeah. Thank you. Please, more question.
Okay, let's see. Online, please, if you want and ask the question.
Okay, so view.
Yeah, I have a question. Thank you very much, Dennis, for an inspiring talk. So in the limit of strong curve of the strong anisotropy, as you said, the curvature effect can be reduced to some effective magnetic field. The form of this field, however, strongly depends on type of anisotropy. Is it easy axial anisotropy with easy axis directed normal to the surface, let's say, or hard axial? So the question is, so these corrections, which comes from the gradient of cross-section area, are they also sensitive to the type of anisotropy, or they are universal?
Yeah, it's correct. Thank you. So I can okay. We analyze both cases. Just for the presentation, I presented one case. So okay. So in both cases there is an effect, but the mathematical formulation is a bit different. So in any case, it's proportional to the gradient of the cross-section or gradient of the thickness in the two-dimensional case, but the prefactor is different. Yeah.
One wait for the microphone.
Thank you for the talk. If we consider spin wave propagation in the system with varied cross-section, then this variant cross-section should work like energy concentrator, changing the magnet density. And in this sense, I would expect some appearance of nonlinear additional terms in magnetic dynamics. So do you see this term, if it comes from already existing energy interaction, or it's something that should be accounted additionally?
Yeah, thank you, Ron, for this question. So yeah, I expect that you are correct, but we have just done a first step, so we did not analyze it up to now. So probably we can do it together. Yeah, thank you. Yeah, please.
Just wanted to ask about the three-dimensional spirals. For which applications they are so promising that you do so complicated shape? How you do?
Yeah, okay. So the idea of three-dimensional these spirals they are used like interconnectors in, for example, in different spintonic devices. So, for example, typically you have even flat two surfaces with some spintonic devices and an interconnector between. If it is three-dimensional, it provides the alter motion of the main walls. Just one example. But also, if we just here you see that three-dimensional racetrack memory, so it's curved. Okay, so and also it's curved, and it also like oops, wait a minute, and also it has a twist. So it's not a spiral, but it's also complicated. And you see these interconnectors; they are also maybe very complicated.
Okay.
Yeah, thank you.
So I think we should move to the next talk. Thank you very much.
Thank you.
For your Volodymyr, can you probably have to stop sharing here?
Okay, should I start? Is everything fine?
Yes, please.
Okay, so thank you for invitation to give a talk. It's a big pleasure to me. So with my colleagues, we study dynamics of magnetic subsystem of altermagnets. And to this end, we developed a tool which we call the Heisenberg models. And today I will show you how we apply this tool in order to consider properties of G-wave altermagnets. And also there is an intriguing question I will explain in my talk. Actually, what do the old streets of Cairo, the capital of Egypt, and altermagnets have in common? So let me first explain what the Heisenberg model is. So here, the best to explain it using the very simple example of a D-wave altermagnet of rutile structure, manganese difluoride, for example, or it can be cobalt difluoride. So if you look only on magnetic atoms here and ignore these red non-magnetic atoms, we just see an antiferromagnet of A type, meaning that we have infinite stack of ferromagnetic layers which couple antiferromagnetically. So what make this structure altermagnetic? This is the position of these red non-magnetic atoms. If we take these positions into account, we see that in order to transform one sublattice to another one, it's not enough to do just a translation by the half of magnetic unit cell and time reversal as for usual antiferromagnet, but one more additional symmetry operation is needed. In this particular case, this is a rotation by 90 degrees above the vertical axis. In more complicated cases, it can be different, maybe a mirror reflection, or rotation can be on different angle. It determines the type of altermagnet. Now, how we take into account in our magnetic Hamiltonian this additional symmetry which comes from location of these non-magnetic atoms? We do it by introducing additional indirect exchanges. So if we look on this top layer, so we can think about indirect super exchange between atoms located on diagonals. And here, due to these non-magnetic atoms, they are located along one diagonal and are not located along the perpendicular diagonal. It means that possible super exchange interactions have to be different. Yeah, and finally, this difference gives us the altermagnetic properties. So this is a simple example just to illustrate how it works. So here we consider two layers of rutile. So we take into account the antiferromagnetic interaction between two sublattices. In addition, we take also ferromagnetic interaction within one layer. And the most important part here, what makes this compound altermagnetic, these additional super exchange interactions within one sublattice, within each sublattice, but they are different in perpendicular directions. They're denoted here J tilde 1 and J tilde 2. So what is important? Yes, they are different in perpendicular direction, but when we go from one sublattice to another sublattice, they rotate by 90 degrees. Yeah, and this circumstance makes this model a D-wave altermagnet. Then we use the classical Landau-Lifshitz equation in order to describe dynamics of magnetic moments. So we have an infinite set of Landau-Lifshitz equations formulated for each magnetic moment. Then we linearize this infinite set in vicinity of the ground state, which is just antiferromagnetic polarization. And use the usual technique based on Holstein-Primakov representation in order to obtain the spectra of spin waves. So this spectra is shown here. Here you see two branches shown by different color. One branch, the difference between branches is different polarization of magnets. Magnum carry magnetic moments. This I will tell you a bit later. And here these moments are opposite, up and down. On the bottom, you see the frequency splitting, so just difference between these bands, and it possesses D-wave symmetry. Okay, so we formulated model, we obtain splitting of the needed symmetry as we expected. So what can we get, which physical effects can we get from this? So here is a list of already physical effects which we predicted using this concept for different materials. And about number of these effects I already reported last year on the same workshop. So just short reminder. So applying this model to D-wave altermagnets, we predicted fluctuation-induced piezomagnetism, and also spin splitter effect for D-wave altermagnetic fields. Also, we considered nonlinear solutions like domain walls. We predicted magnetization induced by altermagnetism for static domain walls. We predicted that when domain wall move in altermagnet, it obtains additional deformation, and its dynamics becomes more complicated. It possesses critical bifurcations like Walker breakdown. Also, if you bend altermagnetic film, it can lead to generation of additional magnetization. Also, for some circumstances, for example, if you have a Dzoloshinsky-Mourier interaction of special time combined with magnetic fields, altermagnetism can lead to generation of Berry curvature, and as a result, we can have topological magnets in system, and we can have thermal Hall effect as a consequence. We have also considered altermagnets of more complicated type, G-wave altermagnets with different anisotropies, chromium antimonide and manganese tellurium. For example, for manganese tellurium, we predicted that altermagnetism leads to generation of magnetic moment for magnets, which is absent for simple, easy planar antiferromagnets. Also, we considered odd parity magnets. And today I will talk about planar G-wave altermagnets, so these results are not yet published. But first, 3 short announcements. So in one talk by one, Kostyantin Yershov will in details explain how magnetization appear in altermagnetic films of different types in response on bending. Tomorrow, Oksana Peshchanskaya will have a poster talk, and she will explain how altermagnetism influences eigenstates of domain wall, which propagates along domain wall. So the new eigenstates can appear due to altermagnetism. And day after tomorrow, on Wednesday, Yulia Guseva will give a talk about altermagnetically emergent spin transport properties in easy planar T-wave altermagnets. Okay, but let's go back to Cairo. So here on the left, you see some photos made on the streets on some south district of Cairo. Yes, you know that it's not possible to fill a plane without gaps by regular pentagons. But there are 15 classes of irregular pentagons which allow such kind of filling, and here you see one example of such pentagons. Remarkably, that one can find these pentagons in nature. So we can find these pentagons in monolayer of pyrit. This compound is also known as fool's gold, and in bulk, its compound is paramagnetic. However, there are works which says that ultra-thin films of this compound can be magnetically ordered, and this is antiferromagnetic order, which appears for relatively for sufficiently small temperatures. So we considered such kind of film. Yeah. Here, big spheres corresponds to iron atoms, and different colors of these spheres corresponds to opposite magnetic polarization of these atoms, up and down, and small spheres corresponds to positions of atoms of sulfur. So what is here important? So if you consider one sublattice and try to introduce indirect exchange between next nearest neighbors. And if you go along these red lines, which are perpendicular here, we see that, if you compare this path along red line and along blue dashed line, we see that they have very different surrounding of non-magnetic atoms. So again, the concept is the same. So in this case, we introduce indirect exchange and assume that these exchanges are different along blue and red lines. And when you compare these directions of these bonds for two sublattices, we see that they are connected by mirror reflection. And now the procedure is the same. We just introduce these additional terms to our Hamiltonian and compute Magnon spectra. Since we have two sublattices, we have two Magnon branches. In this case, we consider easy axial anisotropy, and as for any easy axial antiferromagnet, magnons are polarized up or down differently in different branches. So these different branches are shown by different colors, and the splitting, so just difference between frequencies, are shown here by color, and you can recognize the G wave symmetry here. Yeah, we also did spin lattice simulations and verified our analytical results with full-scale spin lattice simulations. Okay, so we introduced model, we computed the spectra as we expected. So what's good about that? There is one interesting thing about this compound. It's allow a transition from G wave to D wave symmetry under the action of external stress. So last year, this effect was predicted for electron subsystem, for electron spectra. So here people used tie-binding model, and we decided to check if we can obtain the same effect for magnons using our Heisenberg model. So what we did, So let's first consider some stretching applied along these blue arrows. So if it's a stretching, we expect the increase of distance along red and blue lines, which are aligned along this area, and also shortening the distance along perpendicular directions. So in very rough approximation, we can model this effect by changing our altermagnetic exchanges. So this along the stretching will be reduced by some quantity, and this in perpendicular direction will be increased. Now we just introduce this correction to our Hamiltonian and again repeat the procedure of computing the Magnum spectra, obtain the Magnum spectra. Here you can see the splitting. And as we expected, in the region of low energy magnons in vicinity of gamma point, we have some region which has a d wave symmetry of splitting. Yeah? And the size of this region is proportional to square root of our strain. When we apply strain in another direction, in nodal direction, the situation is completely analogous, just different coefficients. But qualitatively, we have the same effect. Okay, why it's good? Because if you have a d-wave altermagnets, we can obtain in so-called spin splitter effect in linear regime. So spin splitter effect is the appearance of spin currents in response to the applied temperature gradient. So this formula, which is written here, can be derived from Boltzmann transport equation in relaxation time approximation. So here, well, actually, what you see here is relaxation time. This is the area of the system. Important quantity staying here is magnetic moment carried by the magnon. We define this moment in the following manner as a derivative of energy of a magnetic field in zero magnetic field at psi minus. This is a general equation. It can be derived when we consider magnetization of the system as a thermodynamical variable, and it's defined very generally as a derivative of free energy of a magnetic field. And when we consider magnons as a Bose gas, ideal Bose gas, one can easily obtain this expression. Actually, it's textbook result. Here we have group velocity. Since we have dispersion, we can compute group velocity and everything we have. So it's just Bose-Einstein factor. Here energy, we have everything. We can compute the conductivity. We did it. So here you can see how this conductivity depends on temperature. Yes, this is a tensor. For this particular case, here we have application of strain in diagonal direction. In this particular case, we have diagonal terms which have opposite sign and no out of diagonal terms. So it's odd in applied stress. I mean, stretching or compression. When we change the sign of stress, we change the sign of conductivity. And here, this is an asymptotic approximation for load in low temperature regime. And what is important here, it's proportional to psi, to the stress. And it's also proportional to altermagnetic parameter. So this delta epsilon is proportional to difference of these altermagnetic J's, yeah, along red and along dashed blue directions. This is the same computation, but stress is applied along a nodal direction. Now we have only out of plane, or only out of diagonal component of conductivity tensor, and actually everything is the same up to coefficient here. Okay, so this was the case of easy axial anisotropy. Yeah, the magnetization, the ground state is perpendicular to the film. What about easy planar anisotropy? In this case, the ground state is in plane. However, direction of this in plane, if you neglect higher order anisotropies, the direction of this in plane ground state can be arbitrary. And this arbitrariness leads to the Goldstone mode. So one of the modes is always is gapless in gamma point, and the second mode is always gapped, and actually these dispersions relations, they do not intersect even without altermagnetism. So altermagnetism leads to some deviation, to some modification of the splitting, but actually they are already splitted. And the sign of splitting is constant here. Okay, in order, but it still must be a G-wave altermagnet, right? In order to see it, we introduce a quantity which we call spin splitter parameter. So this is a product of magnetic moment along the ground state on energy and some over the branches. And this quantity always has the needed symmetry. Magnetic moment here, if you compute it using formula which I presented on previous slide, the expression is quite complicated. Here we present just a simple simplified expression in the limit of very small altermagnetism. What is important is that it's proportional to this altermagnetic parameter. So if you have easy planar antiferromagnet, very simple model, only exchange interaction and easy planar anisotropy, magnets are not polarized. They do not carry magnetic moment. But if it's altermagnetism leads to generation of magnetic moment. And now we can ask ourselves about transport properties, about spin currents. And this is how this spectra in easy planar case looks like in terms of lambda. So you see that this quantities looks the same as splitting of frequencies which we considered for easy axial case. Yeah, and also we computed in the same manner, we computed spin splitter effect. So here on the left you see the results which I have already presented for easy axial case, and this is the easy planar. Here you see that temperature dependence possesses a maximum. This can be explained because now in this easy planar case we have two branches. One branch is always lower than the other one, and of course for small temperatures the contribution from the lower branch dominate and determines the sign and value of conductivity tensor. But with increasing the temperature, higher branch also start to contribute, and the point is, here I did not note it, but this, I noted it. The magnetic moment has different signs. It's K dependent, but for fixed K, for different branches, magnetic moment of a magnet have different signs. So this higher branch now start to, for this reason, the effect is reduced. The contribution is reduced. Here we plotted for different cases, for different directions of application of strain, the relative orientation of a spin current and the applied temperature gradient. So you see that depending on orientation of temperature gradient relative to crystallographic axis, spin current can be parallel, anti-parallel, or perpendicular to the temperature gradient. So if it's parallel, it mimics their back effect, and when it's perpendicular, it mimics Nernst effect. So these effects are for electron systems when spin current appear in response to applied temperature gradient. Here are short conclusions. So we considered the example of period film, monolayer of a period film, and see that it possesses altermagnetic splitting of a planar G-wave symmetry. Applying stress, one can achieve a transition from G-wave to D-wave, and having, at least locally, at least for small energy magnets, a D-wave symmetry, we obtain a magnet-driven spin transport in a linear regime. Linear, I mean the effect is linear in temperature gradient. Yeah, and the next step, we plan to consider nonlinear solutions in these systems like domain walls. We also expect altermagnetically induced magnetization of domain wall with more complicated symmetry, of course. And of course, in these systems, we also expect curvature-induced magnetization. Actually, Kostya Yershov will show you that this is really the case. Okay, thank you for your attention.
Thank you for your talk, Volodymyr. Are there questions either online or Jan, please?
Yeah, thanks for a nice talk. Where do you take the exchange parameters from? Is it from experiment or is it some ab initio estimates?
No, we do not have experimental data for these exchanges. Yeah, since these exchanges are for next nearest neighbors, we actually expect very small. We do not have real numbers. This is just a model. What we demonstrate that in principle it's possible, but we do not know the real numbers for these indirect exchanges.
Like an order of magnitude estimate, what it could be?
Sorry, can you tell it louder? I barely can hear you.
Do you have an order of magnitude estimates how these effects might be large? Or is it really just symmetry based?
I can expect that this is some probably milli-electron volts, but it's poor speculation. I actually don't know.
Yeah, so is the Cairo lattice, is there a material that has antiferromagnetic ordering on the Cairo lattice? I mean, you said that iron disulfide monolayer will do it, but is it experimentally, in fact, realized?
No, it's the paper which I cite here is actually a theoretical paper, so I don't know the experimental paper.
So one might do a calculation, but not experiment at least. Any other questions? Kristian.
So I was wondering what's the relation between this magnetic moment you define and the spin of the magnon, like the spin of a single magnon state.
Okay. Well, I don't know. I mean, we can derive the magnetic moment for magnon using this quite specific formula. But if you are talking about spin means angular momentum. So we need to know somehow gyromagnetic motion or gyromagnetic ratio for a magnon. So I don't know how to really define the spin of magnon. Probably in continuum systems, we can derive it somehow from Noether's theorem. If you have a symmetry, if Lagrangian is symmetrical with respect to rotation above some axis. But this is a question I ask for myself as well, so I don't know the answer.
Good question. Absolutely. Sasha, no? Or...
I think on this third slide, where you show these interactions between sublattices, or you said about interaction between sublattices, but I didn't see it there on this plot. Where is this interaction between sublattices? I mean, between perpendicular, between opposite spins.
Yeah, it's shown here by lines. So this red lines between sublattices JFM. This is
between, but because they connect the same spin directions, and I expected. Okay, I see. Good. So the idea is that they are perpendicular, right? In between, let's say top and next state is one direction, and then they rotated 90 degrees.
Yeah, the idea Yeah, they not only because they are perpendicular, they are different. This is important. In perpendicular directions, they are different. This is one aspect. And when we go from one sublattice to another sublattice, they should be rotated by 90 degrees. So these two facts acting in the same time makes this model altermagnetic, D-wave altermagnetic.
Okay, that was very clear. Thank you again, Volodymyr, for your talk and presentation.
Thank you for the attention and questions.
Okay. Now we go to the next talk, which is also online. Are you there, Igor?
Yep.
Okay, you can share.
Yeah, I'm here. Yeah, okay.
Yes, perfect. So please go ahead.
Yeah, our presentation is devoted to the intrinsic dynamics and eigenmodes of topological spin textures in an antiferromagnet with DMI, Zaloshinsky-Maury interaction. A few opening remarks. Topological spin textures, which is specially localized magnetization configurations, are fundamental and practical applied interest, particularly as potential information carriers in spintronics and magnonics. The antiferromagnets with perpendicular magnetic anisotropy are special promising as they support stable spin textures at room temperature without any external fields. And here a special role is played by Zaloshinsky-Maury interaction, which can induce long period spiral textures in magnets devoid of inversion symmetry, forming chiral structures and magnetic fermions. In such systems, a wide range of topological states arises. For example, including target fermions, axisymmetric multi-ring spin configurations. And fermions exhibit different dynamical regimes, including breathing modes, radius oscillations, rotational modes, core motion, as well as inertial effects. They possess discrete spectrum of bound eigenmodes, and in confined geometries can display controllable oscillations. And while oscillations of ring-like spin textures are in a two sublattice antiferromagnet in the absence of DMI have been studied by us earlier. Dynamics of non-uniform spin textures, especially with an inhomogeneous distribution of inertial mass, remain insufficiently explored. So in this work, we study analytically study eigenoscillations of the topological spin textures in a two sublattice antiferromagnet with DMI. And we study two sublattice AFM with easy-axis magnetic anisotropy in DMI in standard form, and describe and consider anisotropy axis which coincide with the z-axis. And in the absence of external magnetic field, magnetic energy density of uniaxial and AFM with DMI can be written in the following standard form with corresponding constants and corresponding parameters: homogeneous, inhomogeneous exchange energy constant, uniaxial magnetic anisotropy constant, and so on. Further, we start from Landau-Lifshitz equations for the excited states, two sublattice AFM, and come to the equation dynamics for the normalized Néel vector. Further, this equation for Néel vector L can be written as a system of dynamical equations for angular variables theta and phi. And in principle, this system is well-studied system of equations for uniaxial AFM. In such a form was obtained in 1980, 1979 in works of Bayraktar, Ivanov. Parameter C in this system, characteristic velocity, we will use it in our following calculations, and L0 characteristic magnetic length. We will study a special class of 3D nonlinear solutions which derived from this system. They was first derived by Horowitz et al. And should know that the problem of eigenoscillations of topological spin textures and IFM, but without DMI, based on 3D nonlinear solution of this system, was solved by us earlier. Here, we will use this particular solution, 3D spin solution for spin texture, with corresponding parameters for build our theory. Again, C is characteristic velocity. In this case, L0 again characteristic magnetic length, and parameter 0 tilde here is a arbitrary parameter, and it affects only the shift of the spin texture as a whole along the z-axis. And we choose corresponding parameter for magnetic length for our materials, 0.7 nanometers. And can see the turn of the polar angle by theta by minus p occurs, and the thickness of the spin texture is about 5 nanometers approximately. The thickness of the spin texture of this fermion is about 5 nanometers. Our next step is to obtain two key parameters for our theory: the surface mass density of this topological spin texture and surface energy density. And we start from expression for the energy of our texture and use our solution in this equation. Further, for energy density of this spin texture, we divide density in two parts. The first one describes surface energy density, and the second one kinetic energy density. Parameter gamma here plays the role of surface mass density. We can calculate both parameters and obtain our key characteristics, which we need for following: the surface mass density and the surface energy density of the spin texture. Accounting of parameter gamma of density of mass density gamma allows us to estimate the value of the spin texture mass due to its topology. Further and further, we calculate this mass and obtain the corresponding value of it. Further, we can note a very important thing. In fact, schema-mounted spin texture can be described as deformable quasi-particle due to topology of the structure. This is the reason we can calculate separately topological mass. Inertial mass we obtain in other way. And on the next stage, we derived a special equation for this theory. In fact, magnetic skyrmions modeled as rigid solid particles also in both experiments and simulations indicate that they are easily deformable, possessing certain flexibility. Therefore, for axial symmetry, circular flexible spin texture, we can approximate such spin texture, spin texture by a thin, inhomogeneous, non-uniform membrane with variable density. And oscillations of this structure can be described by the following wave equation. Parameter U, function U, characterizes displacement along the anisotropy axis. And further, in the case of free axis symmetric oscillations, this equation can be reduced to the equation for free oscillations of magnetization in this structure. This is equation of the wave equation type, not exactly the wave equation, but equation of the wave equation type with variable coefficient. This you can see here a special coefficient, non-uniform coefficient. Further, in the next step, we formulate the problem of eigenexcitations of the axisymmetric circular spin texture caused by initial perturbations. We can formulate this problem as follows. To find non-trivial solutions of the equation of free oscillations in such a type that satisfies condition of fixing spin isosurface on the circles of inner and outer radii, and the initial radial asymmetric perturbations are due to the degree of freedom related to the deformation of the isosurface. And we assume that the initial perturbations are caused by the following non-coplanar magnetization distribution profile in the form of paraboloid of rotation. And initial velocities we put are equal to 0. Further, the standard form, the standard procedure in dividing our function in two parts. Now we can easily find the solution of the equation for function t for time component, the standard oscillation function, and further the key equation is the Sturm-Liouville problem for the radial complement. We introduce new function, new variable, and come to the equation of the type of the stationary Schrödinger equation with the corresponding potential. Further, again, this equation, and we apply to this equation the quasi-classical consideration, VKB method to this Schrödinger equation. And for the effective wave number corresponding to this equation, we found the isolated turning point and quasi-classical condition can be derived from this theory. And we study ring nanoscale spin as a surface bounded by two concentric circles, which lie entirely in the region of the quasi-classical solution, Schrödinger equation. And in final stage, we obtain the following solution of this equation in this form, and by requiring the fulfillment of the boundary conditions, we find the full set of eigenvalues of this problem. And the solution for the radial component can be written in this form. And final solution of the whole boundary value problem for the ring is a surface, taking account everything: bound eigenvalues, boundary conditions, initial conditions, conditions of orthogonality and normalization, can be written in the following final form. We calculate the corresponding parameters basing on magnetic length 0.7 nanometers, sizes of our ring spin texture, inner and outer radii 25, 50 nanometers, then calculate the value of 10 first coefficients on this series. Last final result is the solution of this boundary value problem normalized to h, it's the amplitude of initial perturbation in the form of paraboloid of rotation. This is the final result and final analytical result, which can be presented in this figure geometrically. Dependence of the ring spin as a surface on the radius and the initial times. In other length scale, we can see it on these figures, and in the corresponding length scale, we can see oscillations here in this video. The last step in our theory is calculation of all dynamical parameters. Our theory, we start from the main tone of oscillations and obtain solution which allows finding each dynamical parameters. Amplitude, frequency, period oscillations. Frequency comparable to the frequency of gyrotropic mode of skyrmion, to the frequency due to inertial effects calculated by numerical simulations, to the frequency of oscillations of domain walls and corresponding confined geometries. Total oscillation energy of the ring spin as a surface can also be written in this case. Parameter m corresponding to the inertial mass of our theory because of axisymmetric oscillations of the spin texture. We can calculate inertial mass of this spin as a surface, it's called 1.6 multiplied by 10 in minus 27 kilograms. should to say that this value of this mass is less than initial mass of skyrmions found in various non-antiferromagnetic materials by different methods, but at the same time as in the ballpark of few electron masses.
Okay, Igor, you have to maybe close the discussion.
Yeah, I'm finishing. Then. Spin texture caused, but its topology can be calculated, and this is the last form, the last result. Again, this topological mass is in line with typical mass scale of skyrmion. In conclusions, we study eigen oscillations of the localized, especially localized non-uniform topological spin texture, and using count of inhomogeneity, obtain an equation of real oscillations of magnetizations, topological spin textures, but with variable coefficients. Quasi-classical solutions allow us to find the axisymmetric circular nanoscale spin configuration and all the main dynamical characteristics, including topological and inertial masses. Key result is that the target skyrmion type AFM spin texture support intrinsic spin excitation mode, so spin texture can perform eigen oscillations. Thank you very much for attention. Sorry for time. Thank you.
Thank you very much, Igor. Thank you for your talk. You stayed more or less on time, but I was not sure that if you would. So if there is a quick question online or in the audience here, we can take it. Otherwise, thank you again, Igor, and we move to the next talk. Thank you.
Thank you very much.
Kostya.
Yeah. Do you hear me?
We do hear you.
Okay, so.
Yes, it's there. Please, next talk, Kostyantin Yershov.
Hello, everyone, and thank you for the possibility of giving a talk on this workshop. Today I will talk about the curvature-induced magnetization of altermagnetic fields. So this work was done in collaboration with Oleh and Khrystyna from Mainz University and in collaboration with Jeroen, Brink and Volodymyr Kravchuk from IFW. So we already had a very nice talk given by Volodymyr and Denis, where we heard a lot interesting things about altermagnets, which effects they can produce, and some curvature-induced effects. And I will not repeat them, but my question was what new effects can generate curvilinear geometry and altermagnetism, which something new or observable effects can be studied there. So in this, we start with a simple model of a thin D-wave altermagnetic film with a crystal structure of a rutile system. The film is bent in the form of the generalized cylindrical surface. This surface can be considered as it can be formed by a planar curve. In our case, we label it as gamma. Gamma is a directrix of our surface. And after that, so the planar curve, it's lie within XY plane, and then we just translate it parallel in the Z direction, and that's how this surface can be formed. On the surface, we introduce a local tangential basis with the vectors E1 and E2. In our case, E1 is the tangential to gamma 1, and E2 is aligned along the Z direction. We also introduce a normal vector E3, which is normal within the whole surface. And additionally, we have curvilinear coordinates xi1 and xi2, where xi1 is an arc length coordinate of the gamma curve. The considered surface has zero Gaussian curvature, and the only one geometrical parameter which describes is this surface is mean curvature. Here prime denotes the derivative with respect to the psi1. And so such a definition of mean curvature corresponds to the maximal curvature on the tops and minimum curvature on the bottoms of the surface. The zero Gaussian curvature means that two-dimensional discrete lattice can be fitted to the curvilinear surface with preserving distances and angles between the neighboring atoms. As a model, as I said before, we consider two square sublattices bounded by antiferromagnetic exchange. We call it J here, and we also introduce next neighboring exchange, which are labeled by J tilde and minus J tilde. And so here we see the symmetry of these bonds. And for different sublattices, this coupling is rotated by 90 degrees. Yes. And additionally, we take into account easy axial anisotropy, which with easy axis aligned along the normal directions. In our case, it's along E3 direction. So, and in the following, we consider the general case when the bending direction, which is defined in our case by psi1, makes an arbitrary angle phi naught with the direction E1 tilde, and E1 tilde here is the crystallographic axis of our system. So we will describe our model in the following within the continuum approximation. In this case, it's convenient to introduce dimensional magnetization vector and dimensional nil vector in the system. The properties of the nil vector, in the limit of the small magnetization, the properties of the nil vector is described by the Lagrangian, which can be considered as a sum of two terms. The first term is common for antiferromagnetic systems, and the last term, the second term, is purely altermagnetic contribution to the system. Yeah. The nil vector obtained from this Lagrangian defines the magnetization of the system. Here we introduce a differential operator D. This differential operator is a differential operator of with respect to the crystallographic axis psi1 and psi2, and we can rewrite it in the curvilinear coordinates in the following way, which takes into account the direction of the bending phi naught. So in the following, we will consider the static case and with the zero field. In this case, the solution for the nil vector is not affected by the altermagnetic contribution. And additionally, the equilibrium solution for the nil vector corresponds to the coplanar state. In this, so it means that the nil vector lie within the xy plane, and it depends only on one coordinate psi1. So we introduce the following parameterization of nil vector, with theta being a polar angle, and the solution for the theta is defined by the driven pendulum equation, where driving force corresponds to the curvature gradient. By using this parameterization for the nil vector, we are able to rewrite the definition for the magnetization of the system. And as we can see from this definition, it is necessary to have deviation of the nil vector from strongly normal direction. In case, for example, if we consider the surface or geometry with constant curvature, for example, regular cylindrical surface, the nil vector for this geometry is always aligned along the normal direction, and the the term in the right-hand side of this pendulum equation vanishes, and we have no magnetization in the system. But if we have non-zero curvature gradient, we observe finite magnetization. In the limit of small curvatures, the solution for theta is defined by the curvature gradient, and we obtain that the magnetization in the system are almost tangential to the surface. Here is the illustration of that sinusoidally banded film, and the top inset corresponds to the distribution of the nil vector, the bottom inset corresponds to the distribution of the magnetization in the system. So the appearance of the magnetization is related to the competition between the non-uniform exchange and easy axial anisotropy, which tracks the geometry. Non-uniform exchange wants to align all wants to have quasi-uniform distribution of the nil vector, while easy axis anisotropy tries to align all nil vector along the anisotropy axis. And these two terms results in the appearance of small areas. It's marked here as yellow one, where nil vector deviates from the normal directions. This deviation results in the appearance of the magnetization in the system. The magnetization vanishes in the extremum points of the curvature. In these points, curvature gradient is equal to 0. But in the between of these extremum points, the tangential component of the magnetization changes the sign, but the transversal component does not, and this results in the non-vanishing transversal component of the magnetization. And in the limit of small curvatures, we are able to calculate how this transversal component of magnetization per period behaves. And we obtain that it is quadratic with respect to the amplitude of the deformation of the film, and it's has a fourth order with respect to the wave vector of the system. So here we cross-checked our analytical results with numerical simulations, and we obtained extremely good agreement. I would say perfect agreement between our analytical calculations and numerical simulations. Here lines corresponds to our analytical predictions, and markers show the results of the numerical simulations. Yeah. So additionally, we considered the G-wave altermagnetic film. In order to model G-wave behavior, we considered next to the next nearest neighbors, as we saw in the talk given by Volodymyr. It has a little bit complicated symmetry, but taking this into account and performing all calculations, we were able to reconstruct the magnetization. The structure of the magnetization is the same, so it doesn't change. The only one difference is the structure of the differential operator. For the G-wave altermagnetic film, this differential operator is of the fourth order. And performing all the same techniques and similar calculations, we are able to get the magnetization. For the G-wave altermagnetic film, the magnetization is still almost tangential to the surface, and in the limit of small curvature, the average transversal component of magnetization per period again behaves quadratic with respect to the amplitude, but for the G-wave, it's of the sixth order with respect to the wave vector curve. Yeah. One should note that as well as for D-wave altermagnetic system and G-wave altermagnetic system. The curvature-induced magnetization is proportional to the altermagnetic coupling. It's encoded with mu alt, and if we do not have altermagnetic coupling in the system, the magnetization vanishes. So in regular antiferromagnetic system, we will see no any magnetic signal. So here is shown the distribution of the curvature-induced magnetization over the sinusoidally deformed stripes for different orientations of the deformation vector Q with respect to crystallographic axis E1 and E2 tilde. With purple lines, we marked the directions with maximal amplitude of the curvature-induced magnetization. And in case if for D-wave and G-wave systems, if we bend our film or stripe in the directions which coincides with crystallographic axis, we don't have any magnetic signal in the end. For the D-wave films, we have only two directions of bending with maximal amplitude, and these directions coincide with the direction of the maximal splitting in Magnon's spectrum for the D-wave system. In the case of the G-wave film, we have four directions, and these directions do not coincide with the directions with the maximal splitting in the Magnon spectrum. Yeah, so these curvature-induced magnetizations open up new possibilities in the investigation of the altermagnets. Namely, due to the rippling of the film, any domain structure of the antiferromagnetically compensated ordering will become visible in the magnetization channel. This is because a geometry-induced part of the magnetization flips the sign under the transformation n to minus n. So if we transform n to minus n, we observe m to the minus m. And as a result, domains corresponding to different ground states acquires the curvature-induced magnetization of opposite signs. Here is the comparison of the numerical simulations for the planar film and for the rippled film. For the planar film, we see that this row shows the nil transversal component of the nil vector, and this one shows transversal component of the magnetization. For the planar system, for the planar antiferromagnetic film, the magnetization only appears due to the gradients of the nil vector, and the induced magnetization is localized in the vicinity of the domain wall position. Moreover, this magnetization has opposite signs on the different sides of the domain wall, which results almost in vanishing stray field. While for the rippled surface, we see that entire domain with opposite directions of the nil vector acquire non-zero finite magnetization. So, and it gives the possibility to use well-developed techniques for ferromagnets, to use them in order to resolve altermagnetic domains via its magnetization pattern. And in conclusion, I would like to mention that a non-zero curvature gradient induces local magnetization that is approximately tangential to the film. The magnitude of the curvature-induced magnetization is determined by the curvature gradient and the direction of the bending relative to the crystallographic axis, and that the maximal effect is achieved when the bending is in the direction of maximum altermagnetic splitting in the Magnon spectrum, at least for the D-wave altermagnet. And thank you for your attention.
Thank you, Kostya.
Is my mic on? Yes, my mic is on.
Yes, yes, I hear you.
Okay. Are there questions? Jan.
Thank you. Nice talk. Is there any connection to piezomagnetism of these effects?
Sorry, I don't hear you.
Is there a connection to piezomagnetism?
We did not consider here the piezomagnetic effects, unfortunately.
Yeah, but you could think in terms of symmetry that you break the fourfold symmetry either by a strain or by
yes, it could be done.
It could be related, right? From symmetry point of view, it might be or not. Okay.
Another one?
Yeah, please.
Can you explain this Lagrangian that you showed, where this altermagnetic part come from?
So the altermagnetic part. So we consider we have this Lagrangian. It, as I said, has two parts. The first part is common for antiferromagnets, and the second one is common for altermagnets, and it's appears due to the symmetry structure of the system. So we start with the lattice Lagrangian, spin lattice Lagrangian, similar to what Volodymyr showed to you, and the different directions of these bonds for different sublattices, and that the symmetry of this altermagnets is related not only with the translation and time reversal, but you also need to have this rotation or inversion operation in mirror inversion operation in the system. So this is the origin on this coupling, which couples next nearest neighbors.
So it is the continuum description of your...
Yes, it's in continuum description.
Altermagnetic model, right? Yeah.
Yes.
Okay, one more question. Oh, there's an online question. We take it first, please. Pablo?
Yeah, hi. Thank you for the nice talk. It's very interesting. So my question is, how do you create this rippled structure? Is it a film that is grown this way, or can I think about dynamically induced curvature, like sound-induced curvature?
So for me as theoretician, I just take it as it is. So I just said that it's done. But there are some experiments as there are different techniques of growing. As Denis showed, you can use Fabit technique, or you can use different evaporation technique when you have substrate and the magnetic material, and then you remove the substrate, and because of the strain you have rippling. Or so that's what I think how it can be done.
Okay. Thank you.
Do you have another question from the audience here? No? Okay, it was the same question. Okay, then we thank you, Kostya, and everybody for the session, and wish you a good lunch.